Right now, without you doing anything at all, the skin of your hand is resting against something soft, and a quiet exchange of forces is happening between the two surfaces, so quiet and so fast that your nervous system has already translated it into a single simple feeling before you had time to wonder about it. You did not have to summon this feeling. You did not have to think your hand into place. It is simply there, the way the sound of your own breathing is there, present and unremarkable, something you could set aside for hours and never miss until someone mentions it, the way I am mentioning it now. Let your hand stay exactly where it is. There is nothing to do here, no posture to correct, no rhythm to match, no effort required of you at all. This is one of those rare situations where the less you do, the more clearly things reveal themselves. So if your eyes are already heavy, let them close, and let the weight of your hand against the fabric become the quiet center of attention for a little while, the still point around which we can wander slowly through a question that turns out to be far stranger and far gentler than it first appears. The question is this: when your hand touches the mattress, or the blanket, or the sheet, what actually happens between them? Not what it feels like, not what your brain reports, what is physically going on, down at the smallest visible edge, and then a good deal smaller than that, in the space where your skin seems to stop and the fabric seems to begin. It is worth sitting with that question for a moment, because most of us go our entire lives assuming we already know the answer. We think of touching as a kind of arrival. Your hand travels through the air, and then it lands, and the landing is the touching, the way a bird lands on a branch, its feet finally making contact with the wood. We picture two surfaces coming together until there is no more space left between them, until the last sliver of nothing has been closed, and that closing, that final meeting, is what we call contact. That picture, it turns out, is not quite what is happening, not because touch is a trick, and not because your hand is somehow failing to reach the mattress. The sensation you're feeling right now is completely real. Nobody is asking you to doubt it. But the ordinary story of how two solid things meet, the story where atoms bump directly into other atoms, the way two marbles might click together on a tabletop, that story does not survive a closer look. And the closer look is worth taking slowly, because it was built by real people, over centuries, mostly by accident, mostly while they were trying to answer completely different questions. Consider for a moment what your hand is actually made of, if you go small enough. Not skin, not cells, but the atoms that build the cells, and within the atoms, a structure that the physicist Ernest Rutherford stumbled onto in 1911, almost by mistake, while a young researcher named Ernest Marsden was firing tiny charged particles at a thin sheet of gold foil in a laboratory in Manchester. Marsden expected the particles to sail through the foil, more or less undisturbed, the way you'd expect a thrown pebble to pass easily through a curtain of smoke. Instead, every so often, a particle would bounce almost straight back, as if it had struck something solid and unyielding. Rutherford later said it was as surprising as firing a 15-inch shell at a piece of tissue paper and having it bounce off and hit you. What that experiment revealed, slowly, over the following years, was that atoms are almost entirely empty space. At the center of each atom sits a tiny, dense nucleus, and around that nucleus, at a distance that is enormous by comparison, electrons exist in a kind of diffuse cloud.
If you shrank an atom down until its nucleus was the size of a marble sitting in the middle of a football stadium, the electrons would be somewhere out near the very last row of seats, and everything in between, all that space, would be empty. No solid matter, no wall, no floor, nothing you could bump your fist against. Just space, and the faint presence of electrons moving through it. So here is the first quiet surprise, and there is no need to hold on to it too tightly, because we will return to it slowly and from several directions before this is over. If atoms are mostly empty space, then your hand, which is made of an almost unthinkable number of atoms, is also, in a strange sense, mostly empty space. And so is the mattress beneath it. Two mostly empty things, resting against each other, and yet you feel something entirely solid, entirely real, entirely there. That is not a contradiction to resolve tonight. It is simply the shape of the question we are settling into, the way you might settle your shoulders a little deeper into the mattress right now, without needing to understand exactly why it feels the way it does, in order to enjoy the feeling itself. I want to be careful here, because it would be easy to take this idea too far, to turn it into the kind of claim that sounds dramatic but says less than it seems to. You may have heard someone say, cheerfully, that you never really touch anything, that everything is illusion, that solidity is a kind of trick the mind plays on itself. That is not quite right, and it is worth setting aside gently before we go any further, the way you might set aside a heavy blanket that turned out to be too warm. The feeling in your hand is not an illusion. The mattress is not imaginary. Solidity is a real property of real things, and it does real work in the real world, holding up buildings, holding up your own body as you lie here. What we are questioning tonight is not whether contact happens, but what contact actually consists of, at the level where atoms and their electrons are the smallest players on the stage. Those are two very different questions, and confusing them is where most of the fogginess about this subject begins. Think of it a little like asking what a river is made of. If someone tells you a river is made of water, that is true, and it is also true that if you looked closely enough at the water, you would find it is mostly the empty space between individual molecules, moving and colliding in ways too fast and too small to see. Neither fact cancels the other. The river is still a river. It still carries boats, still wears down stone, still sounds a certain way against the banks at night. Understanding what it's made of doesn't make the river less real. It just adds a second layer to something you already knew, a layer underneath the surface, the way this conversation is going to add a layer underneath something your hand already knows perfectly well. So as you lie here, hand still resting against the fabric, nothing to solve, nothing to remember, I want you to hold two things at once, loosely, the way you'd hold two thoughts in the last minutes before sleep, when they don't need to be reconciled, only noticed. The first is that the feeling in your hand right now is completely genuine, a real physical event, worth trusting completely. The second is that the story of what causes that feeling is quieter and slower and stranger than the simple picture of two surfaces clicking together like magnets. It involves forces instead of collisions, fields instead of solid little balls, and a kind of resistance that has almost nothing to do with anything actually bumping into anything else. We are not in a hurry to get there. There is no reason to rush toward an answer when the getting there is where the interesting part lives, and when your body, right now, still resting quietly against the mattress, is doing exactly what it should be doing, which is settling, breath by breath, into stillness. In a little while, we'll start with the smallest piece of that empty space, the electron, and the strange invisible cloud it seems to spread itself into, because that cloud, more than anything else, turns out to be the real reason Your hand never quite does what you always assumed it did.
Let's start where your hand actually is, not where the atoms are, because that is the honest place to begin. Your fingertip, resting on the fabric, is covered in skin, and skin is a marvel of layering that most people never think about after childhood, when they learn the word for it and move on. The outermost layer, the one making contact with the sheet right now, is made of cells that are, in a very real sense, already dead. They are flattened, hardened, filled mostly with a tough protein called keratin, and they are constantly flaking away, replaced from underneath by cells that were once soft and living and have since given up their nucleus, their moisture, their machinery, in order to become a kind of armor. This happens to you continuously, all day, every day, without asking your permission or announcing itself. The hand you touched the sheet with an hour ago is not, strictly, the same hand touching it now, not down at the level of individual cells. And yet it is your hand, the same hand it has always been, the way a house is still the same house, even after you've replaced the roof twice and repainted every wall. Underneath that dead outer layer are living cells, and this is where things start to get less solid than they feel. A cell, if you could shrink yourself down and walk into one the way you'd walk into a room, would not feel like a room at all. It would feel more like a harbor at night, dark water full of shapes, moving with purpose, structures drifting and jostling in a fluid that is mostly water itself, the way blood is mostly water, the way you, overall, are mostly water. There is very little in a cell that resembles a wall or a floor. There is a membrane holding the whole arrangement together, thin and flexible, more like the surface tension of a soap bubble than like a brick. Everything inside is suspended, floating, occasionally colliding, endlessly rearranging. Nothing in there is sitting still the way a chair sits still in a room. It's a strange thing to consider, lying here, that the stillness you feel in your hand right now, that sense of quiet, settled weight, is happening on top of a level where nothing is actually still at all. Keep going smaller, past the cell, and you reach molecules, which is really where our story starts in earnest, because a molecule is the first thing on this journey that starts to look less like a structure and more like a rule about how things arrange themselves. A molecule of keratin, or water, or anything else in you, is a specific number of atoms held together in a specific shape, and that shape matters enormously. Shape is, in fact, almost the whole story at this scale. Two molecules made of the exact same atoms in a different arrangement can behave completely differently, can smell different, taste different, poison you, or feed you. This was one of the great surprises of 19th century chemistry, when scientists like Friedrich Wöhler, almost by accident, in 1828, made an organic compound, urea, out of what were assumed to be strictly inorganic ingredients, simply by rearranging atoms in a lab, rather than waiting for a living creature to do it. It suggested, quietly and without fanfare, that life's chemistry wasn't fundamentally different from the ordinary chemistry of rocks and gases. It was the same atoms, arranged differently, following the same rules. And what are atoms, at that point, once you've gone past the molecules that they build? For a very long time, nobody knew, not really, though people had guessed. The Greek thinker Democritus, more than 2,000 years ago, proposed that if you kept cutting matter into smaller and smaller pieces,
You would eventually reach something that could not be cut any further, something indivisible, and he called it atomos, meaning uncuttable. It was a guess, elegant and mostly right in spirit, though he had no way to test it, no instruments, nothing but reasoning and the willingness to imagine an invisible world underneath the visible one. It would take until the early 1800s, with the English chemist John Dalton, for the idea to become something closer to a scientific theory, built from careful measurements of how gases combined in fixed, whole number ratios, as though matter really were made of discrete little units after all, each one behaving like a tiny, solid, indivisible sphere.
For a while,
That image held. A hard little ball. That's genuinely how people pictured the atom for the better part of a century. Something like a marble, small beyond imagining, but otherwise ordinary, solid all the way through. It's a comforting image, honestly, and an intuitive one, because it matches how everything at our scale behaves. But it was wrong, and the way it was shown to be wrong is one of the more elegant experiments in the history of science. In 1909, in a lab in Manchester, England, a physicist named Ernest Rutherford, working with two younger researchers, Hans Geiger and Ernest Marsden, fired a beam of tiny charged particles at an extremely thin sheet of gold foil, so thin it was only a few atoms deep. If atoms were solid little balls packed together, the particles should have mostly bounced off, the way a handful of pebbles thrown at a solid wall bounces back. Instead, almost all of the particles went straight through, as if the foil weren't there at all.
only a very small number, roughly 1 in 8,000, bounced back sharply, at steep angles, some almost straight backward. Rutherford said later that it was as astonishing as if you fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you. That result only made sense if the atom was almost entirely empty space, with all of its mass and positive charge concentrated in an almost impossibly tiny core at the center, what we now call the nucleus. The particles that shot straight through were passing through emptiness. The rare ones that bounced back had happened to strike that tiny dense center directly. If you scaled an atom up to the size of a cathedral, the nucleus would be smaller than a fly buzzing near the ceiling, and yet nearly all of the atom's mass would be packed into that one tiny fly. Everything else, the entire volume of the cathedral, would be occupied by something far lighter and stranger, something we now call the electron cloud. That word, cloud, is doing a lot of careful work, and it's worth sitting with for a moment before we go any further, because it was chosen deliberately to replace an older and simpler picture. For a while after Rutherford's discovery, people imagined electrons orbiting the nucleus the way planets orbit the sun, tiny particles tracing neat circular paths, which is a lovely image and was taught in schools for decades, and is still, honestly, the image most people carry around without ever updating it. But it isn't accurate, and physicists abandoned it, for good reason, within a couple of decades of Rutherford's experiment, once quantum mechanics began to reveal just how strange the behavior of very small things actually is. An electron doesn't travel a fixed path the way a planet does. It doesn't have a definite position at all, not in the way your hand has a definite position on the sheet right now. Instead, an electron exists as a kind of spread-out possibility, a fuzzy region of space, where it might be found if you tried to look, more probable in some places, less probable in others, but never pinned down to a single point, the way we're used to thinking about objects being pinned down. This is strange enough to sit with slowly, without rushing toward the next idea, and it's where we'll pick things up again in a moment, once your breathing has settled a little further into the rhythm it's already finding, because that fuzzy, uncertain cloud,
more than the solid little ball anyone ever imagined, turns out to be the thing your hand is actually resting against.
So let's stay with that cloud a little longer, because before we can understand why it pushes back, we need to understand what kind of thing it's made of. And that means talking about charge, which is one of those words everyone has heard 1,000 times without ever really being told what it means, only that it has something to do with batteries and static electricity and the small shock you sometimes get after walking across a carpet in wool socks. Charge is a property that certain particles have, the way mass is a property that certain particles have, except charge comes in 2 flavors instead of 1. We call them positive and negative, and the naming is almost entirely arbitrary, a choice made by Benjamin Franklin in the 1740s when he was experimenting with the odd behavior of amber and glass and fur, long before anyone knew what an electron was or what a proton was, long before anyone had any real idea what was doing the moving inside these materials when they crackled and attracted little bits of paper. Franklin guessed there was a single fluid involved, and that some objects had too much of it and some had too little, and he called the surplus positive and the deficit negative, and by sheer luck, or perhaps not entirely by luck since he was a careful thinker, the convention he chose has stuck for nearly 300 years, even though we now know the particle that actually moves around in wires and sparks, the electron, was assigned the negative label, which occasionally makes explaining current flow more confusing than it needs to be. But that's a small historical inconvenience, nothing more, and it doesn't get in the way of the deeper idea, which is simple and worth holding on to gently as you drift. Like charges push each other away, and opposite charges pull each other close. 2 negative charges near each other will always repel. 2 positive charges will always repel. A positive and a negative will always attract, reaching toward each other the way your hand reaches, almost without thinking, toward something warm. This rule doesn't bend, doesn't have exceptions we've ever found, and it operates at every scale where charge exists, from the smallest speck of matter up to thunderclouds heavy with static, built from millions of collisions between ice crystals. And the important thing for us right now, lying here thinking about hands and tables and the space between them, is that electrons carry negative charge, every single one of them, identically, without variation, and so does every electron in every atom, in every material your hand has ever come near. This means the electron cloud we were just describing, that fuzzy, spread out, probabilistic haze surrounding each nucleus, isn't just strange and quantum and hard to picture. It's also, everywhere, all the time, negatively charged. The cloud around the atoms in your fingertip is negative. The cloud around the atoms in the countertop, or the blanket, or the pillow beneath your head is negative too, and 2 negative things, as we just said, slowly and gently, always push away from each other. They don't attract, they don't ignore each other, they repel, and the closer they get, the harder that repulsion pushes back. Now, it's worth pausing here, because there's a question that might be forming somewhere in the back of your mind, even as it grows quieter and slower along with everything else, and the question is something like, well, if everything is repelling everything else, why doesn't the whole world just fly apart? Why do atoms hold together at all? Why does anything stick to anything? And the answer is that repulsion isn't the whole story, only the part of the story that matters for touching, for 2 separate objects meeting at their outer surfaces. Inside a single atom,
The negative electron cloud is held close by something else entirely, by its attraction to the positive nucleus sitting at the center, that tiny fly buzzing near the cathedral ceiling we talked about before. Opposite charges attract, remember, and the pull between a nucleus and its own electrons is what keeps an atom from simply dissolving into loose parts scattered through space. So within an atom, there's a kind of quiet balance, attraction pulling the cloud inward toward the nucleus, and other quantum effects we'll get to gently in a later section, keeping the cloud from collapsing all the way down onto that nucleus despite the pull. It's a stable, settled little system, worked out over billions of years of physical law doing the same thing over and over, unchanging, reliable.
But when you bring two separate atoms close together, two atoms that belong to two different objects, say the atoms at the very surface of your skin and the atoms at the very surface of a wooden table, something different happens, because now you're not dealing with one cloud and its own nucleus anymore. You're dealing with two clouds, each negative, approaching each other from opposite directions, each cloud a slightly fuzzy, breathing, probabilistic boundary around its own tiny positive center. And as those two boundaries begin to close, the distance between them, even before anything like real contact could occur, the two negative regions start to feel each other's presence, the way you might feel warmth radiating from a stove before your hand is anywhere near the burner. This is the part I want you to really sit with, slowly, because it's the heart of the whole puzzle we're working through tonight. The repulsion between those two clouds doesn't switch on suddenly, like a wall appearing out of nowhere. It builds gradually, growing stronger and stronger as the distance shrinks, the way the sound of rain grows louder as a storm moves closer rather than starting all at once. When the clouds are still relatively far apart, on the scale that atoms measure distance, the repulsion is faint, almost negligible, easily overcome by the gentle push of your hand moving forward through the air. But as the gap narrows further, the force climbs, and it doesn't climb gently in a straight, even line. It climbs steeply, the way a hill can look like a slope from a distance, and turn out to be nearly a wall once you're standing at its base. The mathematics behind this steepness has to do with how densely packed the negative charge becomes as the clouds start to overlap even slightly. But for now, lying here in the dark, you don't need the mathematics, only the shape of the idea, the sense that this force starts quiet and grows loud very quickly over an almost unimaginably small distance, a distance far smaller than anything your eye could ever resolve. And here's the piece that answers the question we started with, back when we were talking about Rutherford and his foil, and the strange discovery that atoms are almost entirely empty space. The reason the nuclei themselves, those tiny dense flies in their cathedral ceilings, never get anywhere close to touching, is that the repulsion between the outer clouds becomes overwhelming long before the nuclei could ever approach each other. The clouds meet first. They always meet first. And they push back with a force that grows so quickly, so steeply, that it stops the approach cold, translating into what your nerves interpret as solidity, as resistance, as the simple, ordinary sensation of your hand meeting a table. Nothing needs to physically knock against anything else. No hard little spheres colliding like billiard balls for this to happen. It's electric charge, negative meeting negative, growing stronger by the moment as the space between shrinks, that does all the work. It's a strange thought to fall asleep to, that so much of what feels solid in the world is really just this quiet, invisible standoff between clouds of charge that never quite meet, held apart by a force older than any hand, any table, any person who ever wondered about it. And it raises a natural question, one we'll ease into next, gently, without any hurry at all. If nothing ever really meets, what is it, exactly, that decides how strong this pushing feels, and why some things seem to give a little under your touch, while others feel perfectly rigid, no matter how hard you press? The word cloud is a kindness, really, a friendly shorthand that physicists reach for because the actual mathematics resists being pictured at all. When you hear that an electron exists as a cloud around a nucleus, it's tempting to imagine something like fog, a fine mist of electron stuff smeared thin across space, as though the electron had been diluted and spread out the way a drop of ink spreads through water. That image is almost right, and almost right in physics can be its own kind of trap, because the truth underneath it is stranger and, in its own quiet way, more interesting. What physicists actually mean by an electron cloud comes from something called a wave function, a mathematical description worked out in the mid-1920s, largely through the efforts of an Austrian physicist named Erwin Schrödinger, who was, by his own account, trying to find an equation that would make sense of the strange wave-like behavior particles seem to exhibit. A few years earlier, a French physicist named Louis de Broglie had proposed, almost as a hunch, that if light could behave like both a wave and a stream of particles, then perhaps matter could too, that an electron might carry with it something wave-like, a rhythm, a spread, rather than existing as a hard little point. Schrödinger took that hunch and gave it a shape, an equation that could be solved, and out of that equation came these wave functions, one for every possible arrangement of an electron around a nucleus. The trouble was, nobody quite knew what a wave function meant. It wasn't obviously a wave of anything physical, the way a wave in water is a wave of water. It took a German physicist named Max Born, working through the implications not long after, to propose the interpretation that eventually stuck, the one still taught today, though even now, a century later, physicists continue to argue over exactly what it implies at the deepest level. Born suggested that the wave function itself isn't the thing you should picture directly. What you should picture, instead, is what happens when you square it. Mathematically speaking, the result gives you a probability, a likelihood of finding the electron at any particular point in space if you were to go looking. Not a certainty, a likelihood. So when someone describes an electron cloud as denser in some places and thinner in others, they don't mean the electron itself is somehow more concentrated there, the way fog is thicker in a valley than on a hilltop. They mean that if you performed the same experiment over and over, capturing the electron's position again and again, you would find it more often in the dense regions and less often in the thin ones. Imagine, if you can hold the image loosely, a firefly in a dark garden on a summer evening, one you can only ever glimpse for an instant when it flashes. If you stayed out there long enough, watching flash after flash, and marked each spot of light on a piece of paper, a pattern would slowly emerge, a shape built out of hundreds of scattered points, denser in some places, sparser in others. That pattern, that accumulated shape of likely appearances, is something like what an electron cloud represents. Except the firefly, unlike the electron, really was sitting somewhere between flashes, on a leaf, on a stem, waiting. Whether the electron can be said to have a definite location between our glimpses of it is a question physicists still don't agree on, one that touches on some of the oldest and most unresolved debates in the whole field. For our purposes tonight, lying here with your eyes closed, it's enough to know that the cloud is a map of tendency, not a map of stuff. And here's where the shape of that tendency becomes important. A wave function, mathematically, never actually reaches zero. It fades, and fades further, dropping off exponentially as you move away from the nucleus, becoming staggeringly, almost absurdly unlikely at any real distance, but never quite hitting nothing, which means the electron cloud, in the strictest sense, has no edge at all. There's no wall where the cloud stops and empty space begins, the way there's a definite surface where an orange's peel ends and the air around it starts. There's only a fading, a softening, a probability that gets smaller and smaller the further out you go, trailing off the way the last light trails off after sunset, without any single moment you could point to and call the true end of daylight. This is part of why the whole question of touching gets so slippery once you look closely enough. Touching, in the everyday sense, assumes edges. Two things approach. Their surfaces arrive at the same place, and contact happens. A clean event with a clear before and after, like two marbles clicking together on a wooden floor. But if the electron clouds around your fingertip and around the table have no true edges, only fading likelihoods stretching outward forever in principle, then there's no crisp moment where cloud meets cloud, no boundary crossing a boundary. There is only a gradual, continuous increase in overlap, a slow thickening of shared space between two things that were never really bounded in the first place. And overlap itself doesn't behave the way you might expect from watching two clouds of smoke drift into each other and merge. When smoke clouds meet, they blend. They combine into one larger, messier cloud, indifferent to how they got there. Electron clouds don't get to do that so freely, and the reason has to do with another piece of the puzzle, one contributed by an Austrian physicist named Wolfgang Pauli, who in 1925 worked out a principle that still carries his name. Pauli's exclusion principle says, in essence, that no two electrons within the same system can occupy identical quantum states, identical in every measurable respect. It's a rule with no real analog in the everyday world, nothing quite like two people being forbidden from standing in exactly the same posture, in exactly the same room, at exactly the same moment, and yet something like that stubbornness is what happens when electron clouds are pushed to overlap. The electrons can't simply pool together the way smoke does. Their shared mathematical description has to reorganize, has to stretch and shift into new configurations to keep every electron distinct, and that reorganizing costs energy, more and more of it, the more the clouds are forced to overlap. It stacks together with the plain electrical repulsion we talked about a moment ago, charge pushing against charge, to make the resistance climb even more steeply than charge alone would explain. So overlap, at this scale, isn't collision. It's not one thing striking another and bouncing away. It's closer, maybe, to what happens when two voices try to hold the exact same note in a small room, and the room itself seems to resist it, the air thickening with a kind of pressure that has nothing to do with the singers' bodies touching at all. Or maybe it's like two beams of colored light thrown onto the same patch of wall, where the light doesn't collide, doesn't clatter together, it simply layers, and where it layers most thickly, everything about the color and brightness of that patch changes. The electron clouds of your hand and the table are doing something like that layering, one probability distribution folding into another, resisted not because either cloud is a solid thing pushing against another solid thing, but because the shared mathematics of the situation makes deep overlap enormously costly, which leaves us with a picture worth resting your mind on for a while. Two boundless, fading, ever so slightly ghostly distributions, never quite meeting in the marble and marble sense, yet still managing, through charge and through Pauli's strange rule about electrons refusing to share a state, to hold each other at a very definite distance, one your hand can feel every time it presses against wood or stone or skin. And that raises the next question worth drifting toward slowly, the one about why this invisible standoff doesn't feel the same everywhere, why some surfaces yield a little under your fingertip, while others refuse to give at all, no matter how hard you press. Let's slow down on that name for a moment, because it deserves more care than a passing mention. Wolfgang Pauli was a young Austrian physicist, famously sharp-tongued, the kind of person who once told a colleague that a paper wasn't even wrong. It was so far from useful that it didn't rise to the dignity of being incorrect. In 1925, still in his early 20s, he was wrestling with a puzzle that had nothing to do, at first glance, with why your hand doesn't sink into a table. He was trying to understand the pattern of the periodic table itself, why electrons in an atom stack up in shells the way they do, 2 here, 8 there, why they don't all simply collapse down into the lowest, most comfortable energy level and huddle there together, the way a crowd might all shuffle toward the warmest corner of a cold room. Something was stopping them. Something was insisting that each electron in an atom occupy its own distinct quantum state, its own particular combination of energy and orientation and spin, no two ever sharing that exact same set of properties in the exact same system. Pauli didn't yet have a deep mechanical explanation for why this had to be true. He simply noticed, with the kind of unglamorous carefulness that real discovery often requires, that it was true, and he wrote it down as a principle, an exclusion, a rule about identity and difference among certain types of particles. That's worth sitting with, because it's easy to let the word repulsion do too much work here, to let it blur together with the ordinary picture of electrical charges pushing on each other. But the exclusion principle isn't, at its heart, a force at all. It doesn't push. It doesn't pull. It's not made of anything that carries energy across space, the way a photon does, the way the electromagnetic repulsion we already talked about does. It's better understood as a rule about bookkeeping, about the identity of particles, specifically the class of particles called fermions, which includes the electrons drifting through the outer reaches of every atom in your hand and every atom in the table beneath it. Fermions, for reasons that trace back to a deep and genuinely strange piece of quantum mathematics involving how particles behave when you imagine swapping two of them, simply cannot occupy the same quantum state at the same time in the same system. Not won't, in the sense of preferring not to. Cannot, in the sense that the mathematics describing the situation has no way to represent it. It isn't that two electrons in an overlapping identical state repel each other and get pushed apart. It's that a description of two electrons sharing an identical state doesn't exist to be repelled from in the first place. The possibility itself is absent from the accounting. This is a strange kind of prohibition to hold in your mind, especially at this hour, when your thoughts are probably softening around the edges the way they should. Most of the rules
we know from ordinary life are the sort that can, in principle, be broken, even if breaking them costs something, or hurts something, or knocks something over. A rule about not walking through a wall is broken constantly, technically, by every gust of wind that pushes dust and air molecules a little further into the plaster than they were a moment before, even if nothing large ever manages it. But the exclusion principle isn't like a fence you could, with enough force, climb or knock down. It's closer to the fact that a single seat in a small theater can hold one person sitting in it, fully and completely, and cannot also hold a second person sitting in that exact same seat, in that exact same posture, at that exact same moment. You could call that seat's single occupancy a rule, if you like, a kind of prohibition against duplication. But it isn't a force keeping the second person out. It's simply a description of what a seat is, of what occupying a seat consists of. There's no violence in it, and no pushing. There's just no way to fit two identical, complete occupations into the same three-dimensional coordinates and pretend they're one. Now stretch that image a little, because electrons aren't like people settling into a fixed seat with a fixed shape. Each electron state includes its energy level, certain quantum numbers describing its motion and orientation, and its spin, that peculiar quantum property that behaves a little like a tiny compass needle pointing one of two ways. When two electrons in different atoms start to overlap heavily in space, their available quantum states start to overlap too, start to become, mathematically, less and less distinguishable from one another, and exclusion insists, quietly but absolutely, that this cannot fully happen.
So instead of collapsing into shared, identical states, the electrons are forced to spread into higher, more energetic configurations, ones that remain distinct from each other, even while occupying much of the same space. It's a little like two people asked to stand in the same small elevator car, not physically solid enough to block each other outright, but required by some deeper rule to never occupy the exact same posture, the exact same lean, the exact same footing, at the exact same instant. So instead, they contort, they shift their weight, they angle their shoulders differently, they find some awkward but genuine difference in how they occupy the space, and the more crowded the car gets, the more elaborate and costly that contorting becomes. That cost is the important part, because it's what your hand actually feels. Forcing electrons into these higher, stranger, more separated configurations takes energy, real energy, the same kind of energy that shows up as effort, as resistance, as the faint strain you can feel in your fingertip when you press against something solid. And this energy cost rises very steeply as overlap increases, much more steeply than the plain electrical repulsion between charges rises on its own. Charge and Pauli's rule aren't separate walls standing side by side. They're stacked together, compounding each other, so that even a small amount of additional overlap between two atoms' electron clouds produces a large, almost punishing increase in the energy required to sustain it. And it's that steep, unforgiving climb in energy, more than any image of tiny hard shells clacking together, that behaves like solidity. It's not that electrons are small enough marbles bouncing off other small marbles. It's that trying to force too many of them into too little distinct, differentiable space becomes, very quickly, prohibitively expensive,
in the same way that trying to squeeze one more person's completely distinct posture into an already packed elevator becomes, at some point, simply impossible without something giving way. It helps, maybe, to let go entirely of the idea of impenetrability as a property that some tiny object simply has, the way we imagine a steel ball bearing has it. Nothing in an atom is impenetrable in that intuitive childhood sense, the sense of a hard boundary with nothing on the other side of it. What atoms have instead is this deep reluctance built into the mathematics of identical particles against collapsing into indistinguishable states, a reluctance that shows up, from the outside, looking uncannily like firmness, like resistance, like an edge. You could spend a long time turning that thought over without exhausting it, this idea that the solidity under your palm right now isn't a thing at all, isn't a substance, isn't a barrier in the ordinary sense, but a consequence, a kind of emergent stubbornness that arises when countless electrons, none of them touching in any classical sense, are all quietly, mathematically insisting on their own individual distinctness. And once you sit with that for a while, a new question tends to surface on its own, gently, the way it probably has these last few minutes. If this resistance is really about electrons and their overlapping states, and not about any of the atom's protons or neutrons at all, then what exactly is happening deeper down, at the very center of the atom, in that small, dense place the electrons are merely surrounding?
That's a question worth letting sit for now, unopened, resting on the nightstand the way a book does when you're not quite ready to start the next chapter. Because there's a nearer, more immediate mystery still waiting for its answer, the one about your hand and the table, and it deserves to be finished properly before we go looking any deeper into the atom's architecture. So let's come back up to the surface for a while, back to something you can practically feel under your fingers even now, half asleep, and let's talk about what a table actually is, at the level where wood becomes wood and stays wood, night after night, without dissolving or crumbling or forgetting its own shape. Picture, if you can, not the whole table, but a single small patch of it, magnified far past what any microscope could show you directly, though physicists have inferred its structure with remarkable confidence anyway, largely thanks to a discovery made in 1912 when the German physicist Max von Laue realized that X-rays, fired through a crystal, would scatter in a pattern, a kind of shadow lace, that revealed the hidden geometry of atoms arranged in orderly, repeating rows. A crystal, in this sense, isn't a rare gemstone sort of thing. It's just matter that has settled into a pattern, atoms or molecules repeating in 3 dimensions like the same tile, pressed again and again across a floor, extending sometimes for a fraction of a millimeter, sometimes, in the best diamonds, for centimeters without a single flaw. Salt is a crystal, so is quartz. So, in patches, are the metals in a doorknob and the ice in a glacier. Wood is not so tidy. Wood is what botanists call a composite, a tangle of long cellulose fibers, each one itself a kind of twisted, semi-ordered thread, bound together by a stiffer, glassier substance called lignin, the way steel rods are set inside poured concrete to keep a building upright under strain it wasn't otherwise built to take. That's part of why a table can be sawed easily along the grain and only with real effort against it. The fibers were laid down over years by a living tree, each ring a season's worth of growth, thicker in spring when water was abundant, thinner in the dry stretch of late summer, and the tree had no more interest in your comfort at a desk than the sun has interest in warming your particular patch of garden. The pattern just happened to be strong and useful, and someone eventually cut it into planks. But whether we're talking about the orderly repetition of a crystal or the fibrous weave of wood, the thing holding all of it together at the smallest scale is the same kind of relationship we were circling a moment ago. Atoms, sitting near each other, their electron clouds overlapping just enough to create an attraction, without overlapping so much that the reluctance we already talked about kicks in and shoves them apart. Chemists sometimes describe this as the atoms finding a comfortable distance, and that word, comfortable, though a little anthropomorphic, isn't far off. Push the atoms closer than that distance, and the resistance rises sharply. Pull them farther apart, and the attraction pulls back, gently at first, like two people connected by a stretched rubber band. Somewhere in between is a kind of equilibrium, a resting distance, and it's at that resting distance that solid matter quietly organizes itself, atom after atom, into something with a shape that holds. None of this, it's worth saying slowly, means the atoms are frozen still. They're not. Even in the coldest, hardest steel, every atom is vibrating gently around its resting position, a small, ceaseless trembling, faster when the material is warm, slower when it's cold, but never fully stopping, not even, according to the strange rules that govern this small-scale world, at the very theoretical bottom of temperature itself. So a table, however solid it feels, is in some sense a hum, a lattice of atoms quivering in place, like a vast, silent orchestra, holding a single, sustained chord, each musician just slightly out of step with the one beside them, and yet somehow, taken all together, producing something steady enough to hold up a lamp, a stack of books, the weight of a resting arm. Metal behaves a little differently than wood, and it's worth pausing on, because it explains something you've probably felt without ever quite naming it. Why a spoon bends instead of shattering, while a dropped teacup does the opposite. In a metal, the atoms give up their outermost electrons rather generously, releasing them into a shared, roaming cloud that drifts through the whole structure like a fog settled over a valley, no longer belonging to any one atom in particular. The positively charged atomic cores left behind arrange themselves in a lattice, held together not by fixed, directional bonds pointing at specific neighbors, but by their shared attraction to that surrounding electron fog. Because the bonds aren't pointing anywhere in particular, the layers of atoms can slide past one another, under enough force, without the whole structure fracturing. That's why metal is malleable, why a blacksmith can hammer iron into a new shape, why the aluminum in a dented car door doesn't turn into rubble the way a wine glass does. Glass, and here we're stepping into a subject that historically has been more misunderstood than it deserved, doesn't have this luxury, because glass isn't crystalline at all. It's what's known as amorphous, meaning its atoms never settled into a repeating pattern to begin with, freezing instead into something closer to a liquid's disorder, but locked rigid. You may have heard, at some point, that old window panes are thicker at the bottom because glass is secretly still flowing, slowly, after centuries, like an impossibly patient river. It's a charming idea, and it isn't true. The physicist who traced the myth down, decades ago,
found that the unevenness came instead from the imperfect way glass was rolled and installed by hand in past centuries, thicker edges simply set at the bottom out of ordinary practicality. Glass does not flow at room temperature on any time scale that would matter to a human life or 100 human lives. It's rigid precisely because, disordered as it is, its atoms are still locked into that same resting distance from one another, with no easy sliding planes the way metal has, which is exactly why it shatters instead of bending.
Fabric works on a wholly different scale again, not atom against atom so much as thread against thread. Each individual fiber, cotton or wool or linen, itself built from those same cellulose or protein chains, but the real structural trick happening at the level your eye can almost see. Threads crossing over and under one another in a weave, friction and the geometry of the crossing points doing most of the work of holding the whole cloth together, so that a blanket can drape, fold, and stretch in ways a plank of wood never could, without any single fiber needing to bend very far at all. So when your hand finally comes down and rests, unhurried, on the surface of the table, here's what's actually happening, translated out of the electron talk from before and into something closer to plain mechanics. The atoms in your skin approach the atoms in the wood's surface, and as they close that last sliver of distance, the resistance rises, and the table's own lattice responds the way any tension structure responds to a load, bending infinitesimally, the bonds between its atoms compressing by amounts too small to picture comfortably, storing that force the way a coiled spring stores it, and then, because the wood is stiff, pushing back with very nearly the same force your hand is pressing down with, atom by atom, all the way through the plank to the legs, down to the floor. Nothing is torn loose. No atom leaves the table to join your hand. No atom leaves your hand to join the table, at least not under the gentle pressure of a resting palm. Everything simply flexes, ever so slightly, within its own resting position, and springs back the instant the pressure lifts. The wood keeps being wood, the hand keeps being a hand, and the feeling you interpret, immediately and without a second thought, as solid contact, is really that quiet negotiation of pressure and answering pressure, repeated across billions of atoms at once, faster than any thought could follow. Now let's slow down and look at what happens the moment your hand stops merely resting and starts to move, because sliding a palm across that same tabletop introduces a whole different conversation between surfaces, one that has puzzled thoughtful people for centuries longer than you might expect. Leonardo da Vinci, sketching away in his notebooks around the turn of the 16th century, noticed something that seems almost too simple to be a discovery at all, that the force needed to drag one object across another depends on how hard the two are pressed together, and not, oddly enough, on how much surface area is touching. A brick dragged on its wide face resists about the same as the same brick dragged on its narrow edge, so long as the weight pressing down stays the same. That should feel strange if you picture friction as simply more contact, meaning more grip, more square inches of surface rubbing against more square inches. But that picture, it turns out, is wrong in a way that only became clear once people could finally look closely enough to see what a surface actually is. Because no surface, however smooth it looks or feels, is smooth in the way our eyes assume. Polish a piece of steel until it gleams like a mirror, Run your fingertip across it and feel nothing but glassy, uninterrupted flatness, and you have still, at the scale of atoms, produced something closer to a mountain range than a plain. Peaks and valleys rise and fall by distances that would be meaningless to a fingertip, but are enormous to an atom, tiny asperities, as engineers call them, scattered across the surface like a landscape shrunk down past the point where light itself can resolve the bumps. When two such surfaces are pressed together, they do not actually touch everywhere they appear to touch. They touch only at the peaks, at a scattering of tiny points where the highest asperities of one surface happen to meet the highest asperities of the other, and the true area of contact, measured atom to atom, can be a tiny fraction, sometimes less than 1 part in 1,000, of the area your eye would call the touching surface. This is the answer, more or less, to Leonardo's puzzle, worked out properly only in the 20th century by researchers including Frank Philip Bowden and David Tabor, working in Cambridge through the 1940s and beyond. Press two objects together harder, and you don't add more surface area in the everyday sense. You flatten more of those microscopic peaks. You force more of the hidden landscape into contact, and it is the total force squeezing those real contact points together, not the polite fiction of the whole visible surface, that determines how much resistance you feel when you try to slide one thing across another. At each of those tiny points of true contact, something like the same bonding that held your resting hand to the table comes into play, atoms of one surface drawing close enough to the atoms of the other that the same electron clouds that make solid matter solid begin to interact across the gap, weak forces, called van der Waals forces, after the Dutch physicist Johannes Diederik van der Waals, who worked out the mathematics of them in his doctoral thesis back in 1873, long before anyone could see an atom directly, to confirm he was right. Van der Waals forces don't require the sharing or trading of electrons that make a true chemical bond. They arise instead from something more like a flicker, the electron cloud around any atom, shifting and fluctuating in its distribution moment to moment, so that even a perfectly neutral atom develops, briefly, a lopsided arrangement of charge, one side very slightly more negative, the other very slightly more positive. That tiny imbalance can nudge the electron cloud of a neighboring atom into a matching, opposite imbalance, and the two brief lopsidednesses attract each other, weakly, fleetingly, but constantly, since the fluctuation never really stops, it only ever changes partners. Individually, these forces are almost nothing, far weaker than the bonds holding a single molecule together, but summed across millions of atoms crowded into true contact at those microscopic high points, they add up into something you can actually feel resisting your sliding hand. This is also, as it happens, most of the secret behind how a gecko manages to walk straight up a pane of glass, upside down if it likes, without any glue, without any suction, without anything you would recognize as sticking in the ordinary sense at all. Biologists spent a long time assuming geckos must rely on some kind of microscopic suction cups, and it is a satisfying enough guess that it lingered in textbooks for longer than it probably should have, but careful work done in the early 2000s, much of it led by Keller Autumn at Lewis and Clark College, showed something stranger, and in a way, more elegant. Each gecko toe is covered in hundreds of thousands of microscopic hairs called setae, and each of those setae splits at its tip into hundreds of even finer branches, so fine that the very ends approach the scale where van der Waals forces stop being a footnote and start being the whole story. A single one of those branching tips contributes almost nothing on its own. But multiply that nothing
By the billion or so tips a gecko might press against a surface with each step, and the accumulated pull becomes strong enough to support the animal's entire weight, upside down, on glass so smooth it offers the gecko's foot nothing to hook into mechanically at all. The gecko isn't sticking in the way tape sticks, with a chemical adhesive. It is simply getting close enough, at an almost unimaginable number of tiny points, for that same flickering electron attraction to add up into something load-bearing, and then, because the arrangement of those hairs allows the foot to peel away at a particular angle without much effort, releasing that grip step after step without ever getting stuck for good, the way a piece of tape might if you pressed it down too firmly. Tape, for what it's worth, works on a related principle but adds a second trick geckos don't need. An adhesive is typically a soft, slightly gooey polymer, deliberately engineered to be just fluid enough that when you press it against a surface, it doesn't merely touch the high points the way two rigid solids would. It flows, however slightly, into the valleys between them, dramatically increasing that true contact area we talked about a moment ago. More true contact means more of those van der Waals attractions accumulating between the tape and whatever it's pressed onto, and in many adhesives, there is a bit of actual chemical bonding happening too, not just the fleeting electron flicker, but something closer to weak, temporary chemical links forming and reforming across the interface.
Peel the tape away, and you're not breaking one dramatic bond, you're breaking millions of small ones nearly simultaneously, which is why it takes a definite, sudden effort, and why the tape, once removed, often carries a bit of the surface's residue away with it, evidence that the interface, however briefly, was more thoroughly entangled than a casual glance would suggest. Polished glass sits at an interesting extreme of this whole picture, because it is about as close as ordinary materials get to a surface without those microscopic mountain ranges, its structure lacking the orderly repeating lattice of a metal or a crystal, so that when it's ground and polished, the peaks and valleys can be smoothed down to distances measured in mere atoms, rather than the thousands of atoms typical of a rougher material. This is part of why glass feels so distinctively slick, so cold and frictionless under a fingertip, and it is also why two extremely flat, extremely clean pieces of glass or polished metal, pressed together just right in a vacuum, can sometimes bond together almost as if they were welded, a phenomenon engineers call cold welding, the true contact area growing so large, so complete, that the distinction between two separate surfaces meeting and one continuous piece of material starts to blur. Under ordinary conditions, though, out here in an ordinary room, a thin, invisible layer of moisture and oil from the air, and very often a trace of static electric charge as well, keeps most surfaces from ever quite reaching that extreme, which brings us, gently, toward the question of what that charge actually is, and why rubbing certain things together seems to summon it out of nowhere. That question about charge will have to wait a moment, because there's a more immediate mystery sitting right at your fingertips, quite literally, and it has to do with what actually happens in the half-second after skin meets any surface at all, charged or not, smooth or rough, glass or fabric, or another person's hand. You feel something. That much is obvious. But the feeling itself, the specific sensation of pressure or texture or warmth, is not a property that travels up from the object into you like a signal down a wire, fully formed and waiting to be read. It's assembled, piece by piece, out of raw mechanical distortion, and the assembly happens so quickly and so seamlessly that the finished product, the felt experience of touch, gives almost no hint of the manufacturing process underneath it. Start with the skin itself, because before any nerve does anything, the skin has to physically change shape. Press a fingertip against a tabletop, and the outer layer, the epidermis, compresses and shears just slightly, while the layer beneath it, the dermis, stretches and distorts in patterns that depend on how hard you're pressing, how fast, and in what direction. This deformation is not incidental to touch. It is touch, at least at this earliest stage, because the nervous system has no other way of knowing that contact has occurred. There is no sensor anywhere in the body that detects an object is near me directly. Every bit of tactile information starts as mechanical strain in tissue, a literal stretching or squashing of cells, and gets converted from there into something the nervous system can work with. That conversion happens inside specialized nerve endings called mechanoreceptors, and the skin, remarkably, doesn't rely on just one kind. It uses several, each tuned to a different quality of the same physical event. A bit like how a recording studio might use several different microphones, each suited to catching a different frequency range, rather than expecting one microphone to do everything well. Just beneath the surface, in the ridges of skin that form fingerprints, sit Merkel cells, first described by the German anatomist Friedrich Sigmund Merkel in 1875, and these respond best to sustained pressure and fine spatial detail, the kind of information that lets you read Braille or trace the edge of a coin with your eyes closed. They fire steadily as long as pressure continues, giving the brain a running account of still touching, rather than a single burst and then silence. A little deeper, and especially concentrated in the fingertips and lips, are Meissner's corpuscles, named for Georg Meissner, who described them in the 1850s. These respond quickly and then quiet down, which sounds like a limitation, but is actually their whole purpose. They're built to detect change, the onset and offset of contact, the slip of an object beginning to move across skin, rather than the fact of contact continuing. This is part of why, if you rest your hand very still on a surface, the sensation of touching it seems to fade, even though nothing about the physical contact has changed. The receptors that would normally shout about it have already said what they needed to say and gone quiet, waiting for the next change to report. Deeper still, wrapped in layers that look, under a microscope, uncannily like the cross-section of an onion, are Pacinian corpuscles, structures first noticed by the German anatomist Abraham Vater in the 1740s, and then rediscovered and more thoroughly described a century later by the Italian anatomist Filippo Pacini, whose name they now carry, in one of those small historical asymmetries where the second discoverer gets remembered and the first mostly doesn't. Pacinian corpuscles are exquisitely sensitive to vibration, and their layered structure acts almost like a mechanical filter, smoothing out steady pressure so that only rapid, oscillating changes get through to the nerve fiber at the center. This is the receptor, doing much of the work when you feel the buzz of a phone through a table it's resting on, or the fine grain of sandpaper, which your fingertip reads less as a static shape and more as a rapid vibration as it moves across the tiny ridges. And there are Ruffini endings, associated with stretching of the skin itself rather than direct pressure, useful for sensing the shape your hand is making and the way skin pulls when a joint bends, contributing to something the body needs constantly but rarely notices consciously, an ongoing sense of where the skin, and by extension the limb beneath it, actually is in space. Temperature runs on an entirely separate system, which is worth pausing on because it explains something that might otherwise seem strange, namely why a numb patch of skin, from cold or from a local anesthetic, can sometimes still register pressure while losing the sense of warm and cool almost entirely, or the reverse. In the late 1800s, the physiologists Max von Frey and separately Alfred Goldscheider and Magnus Blix discovered something that must have been startling at the time, that if you map the skin with a fine cold probe and then with a fine warm probe, you don't get sensation everywhere uniformly. You get scattered points, cold spots and warm spots, distinct locations that respond preferentially to one or the other, as though the skin were dotted with separate switches rather than being uniformly sensitive to temperature everywhere at once. Later work identified specific nerve fibers and more recently, specific molecular channels responsible for this, distinct from the mechanoreceptors handling pressure, which is why temperature and touch, though they arrive from the same patch of skin, are genuinely separate channels of information, processed side by side rather than blended together at the source. Pain works differently still, and its receptors, called nociceptors, are deliberately unspecialized in a way the others are not. Rather than being tuned finely to one kind of stimulus, they respond broadly to anything intense enough to threaten tissue, whether that's extreme pressure, extreme heat, extreme cold, or certain chemical irritants, treating all of them as variations on a single message worth escalating urgently. This is why a burn and a deep bruise and a chemical sting can all register as recognizably painful, despite being caused by such different physical events. The receptor isn't identifying the specific cause so much as flagging the general category, tissue in danger, and letting later processing sort out what actually happened. All of this, the pressure signals, the vibration, the temperature, the pain, converts at its source from mechanical or thermal energy into electrical impulses traveling along nerve fibers, and here the body reveals another bit of quiet engineering, because not all of these signals travel at the same speed. Fibers carrying sharp, precise, urgent information, fine touch, the sting of a fresh cut, tend to be thicker and often wrapped in an insulating sheath called myelin, letting impulses race along at speeds up to roughly 100 meters per second. Fibers carrying duller, slower pain, the aching throb that follows an injury, rather than the initial sharp jab, are thinner and unmyelinated, conducting at a fraction of that speed. This difference is why stubbing a toe often produces two distinguishable waves of unpleasantness, a sharp jolt arriving first, followed a moment later by a slower, heavier ache. Two separate signals from the same injury, arriving at noticeably different times, because they were never traveling at the same speed to begin with. From the skin, these signals travel up through nerves, into the spinal cord, and even here, before the brain gets involved at all, some sorting, and even some decision-making, already happens. The knee-jerk reflex, or the reflexive pulling away from something painfully hot, is coordinated largely within the spinal cord itself, a loop that can act before the signal has even finished its longer journey up to conscious awareness, which is part of why you can find your hand already withdrawn from a hot stove before you've consciously registered the word hot at all. Only after this local processing do the signals ascend further, through pathways with names like the dorsal column and the spinothalamic tract, each carrying a different flavor of sensation, up toward the brain by a slightly different physical route, eventually arriving at a strip of the brain's surface known as the somatosensory cortex, where, remarkably, the body is mapped out in miniature, though not proportionally. And it's in the shape and strange proportions of that map, oversized hands, oversized lips, a comparatively tiny torso, where the story of touch stops being about nerve endings entirely,
and starts becoming a story about how much brain real estate we've each been given to actually notice ourselves.
Let's step away from the map inside the brain for a while and wander instead toward the edges of what we even mean by the word touch, because some of the strangest cases aren't about biology at all, but about physics quietly refusing to behave the way our intuitions expect. Consider water. When you dip your hand into a basin, you feel wetness immediately, a cool, clinging sensation that seems obviously like contact, maybe the most contact-like thing there is. But wetness itself is not a fundamental property of water, the way mass or charge are fundamental properties of matter. Wetness is an experience your nervous system constructs from a combination of cues: temperature change, the mechanical pressure of the liquid's surface tension pulling at hair follicles and skin, and the way water conducts heat away from your skin roughly 25 times faster than air does. There is no dedicated wetness receptor anywhere in your skin. Instead, thermoreceptors and mechanoreceptors fire together in a particular pattern, and your brain, drawing on a lifetime of experience, interprets that pattern as wet. This is why, if you close your eyes and someone touches a cold, dry metal object to your skin, you may swear, quite confidently, that it feels wet. The metal pulls heat away rapidly, mimicking part of the signature that water usually produces, and your brain, working from incomplete information as it always does, fills in the rest with its best guess. The wetness you feel so certainly is, in a very real sense, an inference, a story your nervous system tells rather than a direct readout of some liquid property being detected. And even setting aside the question of how wetness is perceived, there's the deeper question of what's actually happening at the surface where water meets skin. At that boundary, we're back to the same story as before, the same electron clouds repelling one another, the same electromagnetic cushioning that keeps a fingertip from ever truly touching a tabletop. Water molecules, held loosely together by hydrogen bonds, a particularly clingy form of intermolecular attraction where a slightly positive hydrogen atom on one molecule is drawn to a slightly negative oxygen atom on its neighbor, press against the outer layer of your skin cells without their electron clouds ever actually merging with your own. The sensation of wetness, then, is doubly indirect, an inference built from signals generated at a boundary where nothing is truly touching anything else in the first place. Air pressure offers a different kind of puzzle, because most of the time, we don't feel it at all, despite being submerged in a fluid, the atmosphere, that presses against every surface of our bodies with a force of about 14 pounds per square inch at sea level, which works out to something in the neighborhood of 20,000 pounds of total force, pressing on an average adult body at any given moment. We don't collapse under this weight, and we don't feel crushed, because the pressure is balanced. The fluids inside our bodies push outward with nearly equal force, and because the pressure is uniform, arriving from every direction at once, and largely unchanging from moment to moment, our mechanoreceptors, which are specialized to detect change rather than steady states, simply stop reporting it. This is a general feature of how nervous systems work, called sensory adaptation, and it shows up everywhere, from the way you stop noticing the feeling of clothing against your skin a few minutes after getting dressed, to the way a constant background hum in a room fades from awareness within moments. Air pressure becomes noticeable only when it changes rapidly or unevenly. The ache in your ears during an airplane's descent, the muffled thump you feel in your chest standing near a large speaker at a concert,
the sudden pop when a mountain pass gains enough elevation to matter. In each case, what you're sensing isn't pressure itself so much as a mismatch, pressure pushing unevenly against different surfaces of your body, particularly the eardrum, which is thin and sensitive precisely because it needs to register vibrations far too small and far too fast for skin to bother with. Which brings us naturally to sound, because sound is really just organized pressure changes moving through a medium, whether that medium is air, water, or solid matter, at speeds that depend heavily on how tightly packed and how strongly bonded the underlying particles happen to be.
Sound travels through air at around 343 meters per second, but through water it moves nearly 4.5 times faster, and through steel faster still, over 5,000 meters per second, because in denser, stiffer materials, each particle can hand off its jostling motion to its neighbor more quickly, without needing to first drift across empty space, the way gas molecules do. This is why, in old stories, people are described as pressing an ear to a train track to hear an approaching train long before it becomes audible through the air, and why submerged swimmers can sometimes hear sounds from remarkably far away, sounds arriving through the water itself. What's worth pausing on here, in a section devoted to the strange edges of contact, is that sound is nothing but touch, relayed at a distance, an unbroken chain of tiny electromagnetic pushes and pulls between neighboring particles, none of which ever fully merge, passing a disturbance along like a long line of people, each nudging the shoulder of the person ahead. You never touch the person speaking to you across a room, not in the sense of your skin meeting theirs, and yet their voice arrives at your eardrum as a genuinely physical, mechanical event, a wave of real pressure fluctuations that started as the vibration of their vocal cords and traveled the intervening distance as an unbroken relay of contact between molecules that were never, themselves, in contact with you. Magnetism complicates the picture even further, because a magnet pushing or pulling another magnet across open space seems, on its face, to violate the whole framework we've built up, this idea that force requires some mediating field, some invisible messenger crossing the gap, and in a way, it does require exactly that, just not one made of matter. A magnetic field is a genuine physical thing, filling the space around a magnet, capable of doing measurable work, capable of being mapped by iron filings, sprinkling themselves into visible curved lines around a bar magnet, and yet it isn't made of particles that bump into other particles the way air molecules do. It's better understood as a condition of space itself, a strain or configuration that a moving or spinning electric charge sets up around itself, and that other charges, in turn, respond to. When you hold two magnets close enough to feel them tug at one another, you aren't wrong to feel that something real is happening between them, but the something is a field, not a substance, and the interaction is mediated, at the deepest level physicists currently understand, by the exchange of particles called photons, the very same particles responsible for light itself, passing back and forth between the magnets in a constant, invisible negotiation. This is, in its own way, no stranger than the electromagnetic repulsion between electron clouds that prevents your hand from passing through a table, just more dramatically felt, more clearly demonstrable, because you can watch the force act plainly across a visible gap, rather than being hidden entirely within a boundary so thin it might as well be non-existent. Vacuum offers perhaps the cleanest illustration of how strange all this becomes once you push toward the extremes. In the near-perfect emptiness of space, far from stars and planets, there is almost nothing left to touch at all, not in any conventional sense,
No air pressing against a spacesuit, no medium to carry sound, which is why explosions in the vacuum of space, so thunderous in film, would in reality be silent, there being no particles nearby to relay the pressure wave to an ear that also, incidentally, wouldn't be there to hear it. And yet even a vacuum isn't quite the absence of everything modern physics once imagined it to be. Quantum theory suggests that even in the emptiest possible stretch of space, fields still exist, fluctuating, capable in principle of producing detectable effects, a phenomenon still actively studied, and in some of its subtler predictions, still debated among physicists rather than fully settled. It's a reminder that even our best word for total absence, vacuum, turns out to be more textured, more populated, than the everyday sense of the word implies. And then there is superfluidity, a state of matter strange enough to make ordinary liquids look almost tame by comparison. One more waypoint before returning, gently, to the more familiar territory of the body.
The idea that matter might be made of tiny, indivisible pieces is older than almost any other scientific idea still taken seriously today. Older by roughly 2,000 years than any instrument capable of testing it. In the 5th century before our era, in the Greek colonies along the Aegean, a philosopher named Leucippus and his student Democritus proposed that if you kept cutting a piece of matter in half again and again, you would eventually reach something that could not be cut any further, a smallest possible unit, which they called atomos, meaning uncuttable. They had no way to see one, no way to weigh one, no experiment that could confirm or deny the idea. It was a guess, elegant and stubborn, built from pure reasoning about what seemed logically necessary rather than anything observed, and for a very long time it lost. Aristotle, whose authority shaped Western thought for nearly 2,000 years, preferred a different picture, one built from 4 continuous elements, earth, water, air, and fire, blending into one another smoothly, rather than being assembled from discrete grains. Atomism survived mostly as poetry, most famously in the Roman poet Lucretius's long verse work on the nature of things, admired more as literature than as physics, quietly waiting. It would take until the early 1800s and a quiet, half-deaf English schoolteacher named John Dalton for atomism to re-enter science with actual evidence behind it, not proof exactly, but something closer than the Greeks ever managed. Dalton was studying the weather, of all things, tracking barometric pressure and the composition of the air, when he became fascinated by the fact that when different elements combine to form compounds, they always do so in fixed, whole number ratios, never in some smooth, continuous range. 2 parts of this to 1 part of that, consistently, as if matter really were made of countable units, combining in tidy proportions, rather than pouring together like 2 liquids mixing freely. It was indirect evidence, inferred from chemistry rather than seen directly, but it was evidence, and it gave the old philosophical guess a foothold in laboratory measurement for the first time. The next real crack in the mystery came not from chemistry, but from electricity, a force that nobody in Dalton's era fully understood either. Michael Faraday, working at the Royal Institution in London in the 1830s, ran currents through chemical solutions and noticed that the amount of a substance deposited or dissolved during electrolysis was always proportional to the amount of electric charge that passed through it, in fixed, discrete amounts. It was another hint, largely unremarked at the time, that electricity itself might come in units, might be made of countable pieces rather than being an infinitely divisible fluid. That hint sharpened considerably in 1897, when J.J. Thomson
experimenting with cathode ray tubes at Cambridge, essentially glass tubes with most of the air pumped out and a high voltage applied across them, found that the mysterious rays glowing inside could be bent by electric and magnetic fields, and that whatever was doing the bending carried negative charge and was thousands of times lighter than the lightest known atom. He had found a piece of the atom, a particle smaller than the supposedly uncuttable thing, which he named the electron, and which forced everyone to admit that atoms, whatever else they were not the final answer after all. Around the same time, an entirely different line of investigation was quietly closing in on the same target from a completely different angle. In 1814, a German optician named Joseph von Fraunhofer, testing the quality of glass lenses, pointed a prism at sunlight and noticed something strange, a series of dark lines cutting across the otherwise smooth rainbow of colors, as if certain wavelengths of light were simply missing. He catalogued hundreds of these lines without knowing what caused them. It took until 1859 for two other Germans, the chemist Robert Bunsen and the physicist Gustav Kirchhoff, working together in Heidelberg, to realize that each chemical element, when heated until it glowed, gave off light only at its own particular set of wavelengths, a kind of fingerprint, and that the dark lines in sunlight were caused by those same elements in the sun's outer layers absorbing exactly the wavelengths they would otherwise emit. Suddenly it was possible to know what a star was made of without ever visiting it, just by reading the pattern of light it sent across empty space, and it hinted, faintly, that whatever was happening inside atoms to produce those fixed, sharp lines was itself happening in fixed, discrete steps, rather than smoothly and continuously. The picture of the atom's actual architecture came into focus in 1911, in Manchester, when Ernest Rutherford asked two of his students, Hans Geiger and Ernest Marsden, to fire a beam of small charged particles at an extremely thin sheet of gold foil, only a few atoms thick. Almost all of the particles passed straight through, exactly as expected if atoms were mostly empty space, but every so often, roughly 1 in 8,000, a particle bounced almost straight back, as if it had struck something small, dense, and heavy at the atom's center. Rutherford later said, "It was as astonishing as firing a 15-inch artillery shell at tissue paper, and having it bounce back at you." From that experiment came the modern picture of the atom, a tiny, dense nucleus, carrying almost all the mass, surrounded by a vast, mostly empty volume through which lighter electrons moved. 2 years later, the Danish physicist Niels Bohr proposed that those electrons could only occupy specific, fixed orbits around the nucleus, jumping between them in sudden steps, rather than drifting smoothly, absorbing or releasing light of very particular wavelengths as they did, which finally explained why Fraunhofer's dark lines and Bunsen and Kirchhoff's glowing fingerprints looked the way they did. The lines were discrete, because the jumps were discrete. Bohr's model, elegant as it was, still treated electrons as tiny orbiting particles, like miniature planets, and that picture didn't survive much longer.
In 1924, a French physicist named Louis de Broglie proposed in his doctoral thesis the startling idea that particles of matter might also behave like waves, an idea so unusual that his examiners reportedly consulted Einstein before agreeing to accept it. 3 years later, at Bell Labs in New Jersey, Clinton Davison and Lester Germer confirmed it almost by accident, firing electrons at a crystal of nickel and finding that they scattered in a pattern that could only be explained if the electrons were behaving like waves of light diffracting through a fine grating, spreading and interfering with themselves. Electrons, it turned out, were neither simply particles nor simply waves, but something that didn't map cleanly onto either everyday word, and the neat little orbits of Bohr's model gave way, through the work of Erwin Schrödinger and Werner Heisenberg in the mid-1920s, to the modern picture of electrons as spread-out clouds of probability, present everywhere and nowhere in particular until measured. For most of the 20th century, that remained the outer limit of the story, a mathematics that could predict how atoms behaved without anyone ever actually seeing one directly, atoms being so much smaller than the wavelength of visible light that no ordinary microscope, however finely ground its lenses, could ever resolve one. That changed in 1981 at IBM's research laboratory in Zurich, when two physicists, Gerd Binnig and Heinrich Rohrer, built a strange new kind of instrument, one that didn't use light at all. Instead, it dragged an unimaginably fine metal tip, sharpened in places to a single atom's width, across a surface at a distance of less than a nanometer, close enough that electrons could tunnel, in the quantum sense, between tip and surface, and by tracking the faint resulting current with exquisite precision, the instrument could trace the bumps and valleys of individual atoms the way a blind reader's fingertip traces the raised dots of Braille. For the first time in human history, atoms could be seen, after a fashion, not with light, but with touch, translated into current, translated finally into an image. Binnig and Rohrer won the Nobel Prize for it in 1986, and their instrument, the scanning tunneling microscope, opened a door that had been sealed since Democritus first imagined the uncuttable thing, without any hope of ever confirming it. Let's leave the surface of ordinary matter behind for a while, and go somewhere the electron cloud cannot hold its shape no matter how hard it tries. The center of a planet, the corpse of a sun, the crushed remnant of a star that once outweighed everything you have ever seen in the night sky. Start with something familiar, something you can almost feel in your own hands as you drift. Think of the way a mattress pushes back when you lie down on it, sinking just enough to cradle you, and then refusing to sink any further. Or think of a stack of books on a shelf, how you can press down on it with your whole weight, and the books will not compress into a smaller stack, no matter how hard you lean. That resistance, the ordinary, everyday refusal of solid things to occupy less space than they already do, comes from electromagnetic repulsion, the same story we have been circling all along. Electron clouds shouldering other electron clouds aside, politely but absolutely, the way two crowds moving through a narrow hallway in opposite directions will bump shoulders rather than pass through one another. It is a remarkably strong force at the scale of a hand pressing a table, strong enough that you have never once, in your entire life, pushed your palm flat through a slab of granite, or watched your coffee cup sink slowly into your desk overnight. But it is not, it turns out, the strongest form of resistance matter is capable of, and there is a limit to how hard even a planet can squeeze before something else entirely takes over the job of holding the walls up. Descend, in your mind, toward the center of the earth. Not by drilling, since no drill has ever gone deeper than about 12 kilometers, a scratch on an orange peel, compared to the 6,371 kilometers separating the surface from the core, a depth so far beyond our reach that the deepest borehole ever made, the Kola Super Deep borehole in Russia, took nearly 20 years to inch that far and still amounted to less than 1/5 of 1% of the way down. So descend instead by following the pressure as it mounts, layer by silent layer. At the boundary between Earth's mantle and its core, roughly 2,900 kilometers down, the pressure is already something like 1.5 million times what you feel standing at sea level, more force per square inch than exists anywhere on the surface of any world humans have ever visited. By the time you reach the very center, it climbs past 3.5 million atmospheres, an unfathomable, silent, crushing weight,
the entire mass of the planet bearing down from every direction at once, evenly, patiently, without any of the drama the number itself might suggest. And yet the iron there is still, in the everyday sense, iron. Its electrons are still repelling their neighbors' electrons the ordinary way, just squeezed into somewhat tighter formation, their clouds compressed the way you might compress a sponge underwater, still springy, still recognizably electromagnetic in its resistance, just working at a scale of effort almost impossible to picture. This is why the inner core, despite pressures that would flatten a submarine like a sheet of paper, is thought to be solid rather than liquid, the iron atoms packed so closely together that they crystallize even at temperatures approaching that of the sun's surface, temperature and pressure locked in a strange tug-of-war, that pressure, at the very center, narrowly wins. But planets, on the scale of what the universe is capable of building, are gentle places. Follow the pressure further, out past Earth entirely, to the kind of density found inside a white dwarf, the smoldering leftover core of a star like our own sun, after it has spent its nuclear fuel and shed its outer layers into space, a slow and almost graceful process our own sun will undergo in roughly 5 billion years, according to models astronomers have built from patiently watching thousands of similar stars complete the same transformation across the galaxy. A white dwarf packs something close to the entire mass of the sun into a sphere roughly the size of the Earth, which means the ordinary electron cloud resistance that holds up a planet's crust, or a person's shin bone, or a stack of books on a shelf, is being asked to perform an entirely different order of work.
And at some point, it isn't quite equal to the task, not in the way you would expect from simply scaling up what happens inside a planet. The electrons get squeezed so close together that the everyday picture of independent little clouds bumping and repelling one another like crowds in a hallway dissolves into something else entirely. This was worked out mathematically in 1926, remarkably quickly after Schrödinger and Heisenberg had finished laying the foundations of quantum mechanics, by the physicist Ralph Fowler, who realized that a rule discovered just a year earlier by the young Austrian physicist Wolfgang Pauli, a rule originally invented merely to explain patterns in atomic spectra, patterns of colored light emitted by heated gases, had a far stranger and grander implication than anyone had first suspected. Pauli's rule, now called the exclusion principle, says that no two electrons can occupy exactly the same quantum state at the same time, the same combination of position and momentum and spin, described in the language of quantum mechanics. In an ordinary object, this rule matters, but it is not the dominant source of resistance, because the electrons have plenty of room to arrange themselves into different states without much fuss, the way a nearly empty theater lets people spread out across many rows without anyone touching. But inside a white dwarf, where matter has been compressed to roughly 1,000,000 times the density of water, so dense that a single teaspoon would weigh as much as a small car, the electrons run out of room, the theater fills completely, and there are no empty seats left. They cannot all crowd into the lowest energy, most comfortable arrangement, because the exclusion principle forbids it, and so they are forced, whether they have any excess energy or not, into higher and higher energy states, moving faster and faster, simply because there is nowhere calmer left to be. This forced motion, called electron degeneracy pressure, has nothing to do with heat, nothing to do with temperature in the ordinary sense, and nothing really to do with electromagnetic repulsion either, though the two are often lumped together in casual explanation. It is instead a direct, almost stubborn consequence of quantum statistics, electrons refusing, as a matter of the deepest rule they obey, to share an address. It is this pressure, and not the ordinary electric repulsion that holds up a tabletop, that keeps a white dwarf from collapsing further under its own gravity, a discovery so unexpected that when the young Indian physicist Subrahmanyan Chandrasekhar worked out its consequences in detail a few years later, during the long sea voyage from India to England in 1930, using nothing more than pencil, paper, and the quiet hours of a ship crossing the ocean, he found that even this stranger, more stubborn resistance has its own limit, a mass beyond which even degenerate electrons cannot hold the line. Beyond that limit, in stars considerably more massive than our Sun, gravity wins even against the exclusion principle's electrons, and something more drastic happens. The collapse continues until the electrons are forced to merge with protons, a reaction that produces neutrons and releases a flood of nearly massless particles called neutrinos, streaming outward through the collapsing star, almost as if the matter around them barely existed. The star's core is transformed, in a matter of seconds, from ordinary atomic matter into something almost unimaginably strange, a neutron star, an object typically no wider than a modest city, perhaps 20 kilometers across, and yet containing more mass than our entire Sun. Here it is degeneracy pressure again, but this time belonging to neutrons rather than electrons, that holds the collapse from going further, the same Pauli exclusion principle now applied to a different family of particles, refusing to let neutrons pile into identical states, no matter how ferociously gravity insists otherwise. A teaspoon of neutron star material, if you could somehow scoop one out and set it gently on a kitchen counter, which you emphatically could not do, would weigh something like 1 billion tons, roughly the mass of a mountain compressed into a space smaller than a sugar cube, sitting there in perfect, terrible silence. It's worth pausing here, in the quiet, to notice what has actually changed, moving from a planet's core, to a white dwarf, to a neutron star, because it is easy to blur these into one vague idea of things simply being squeezed tighter and tighter. What changes is not merely how hard something is being pressed, but which physical principle is doing the resisting. In the planet, ordinary electromagnetic repulsion between electron clouds, the same force that stops your hand from passing through a wall, or your body from sinking through a mattress, is doing essentially all the work, just under far greater duress than it ever experiences at the surface. In the white dwarf, that force has been overtaken by quantum degeneracy pressure, a resistance rooted not in charge, but in the sheer unwillingness of identical particles to share a state, a rule about identity rather than about push and pull. And in the neutron star, that same statistical stubbornness has migrated from electrons to neutrons, while a separate and even stranger force, the strong nuclear force, the one that binds protons and neutrons together inside every atomic nucleus you have ever been made of, begins to make its own quiet contribution to holding the whole structure together against gravity's relentless, patient pull. And yet none of that vast distance matters very much right now, because you are not made of neutron star material, and you are not floating in the crushing dark between collapsing suns. You are here, in a bed, in a room, at the end of a very long and very patient explanation, and the thing that explanation was always circling back toward, however far it wandered into stellar cores and strong nuclear forces, was the simple, ordinary fact of a body resting on a mattress. So let the neutron stars recede now, the way a train you were once riding recedes into the distance while you stay standing on the platform. Let your attention come home to something much smaller and much closer, the weight of a blanket, the give of a pillow, the particular pressure of a mattress meeting your shoulder blades, your hip, the back of your skull. And here is the thing worth sitting with, now that the whole long chain of explanation has been laid out. Everything you have heard across this entire telling, the electron clouds that never quite meet, the electromagnetic fields that repel before anything solid ever arrives, the degeneracy pressure that holds up dying stars, the strange choreography of nerve endings translating pressure into signal, the fact that your brain is, in a very real sense, constructing the sensation of touch from electrochemical patterns rather than receiving it as some raw, unmediated fact. None of that makes the touch less real. This is perhaps the single most important thing to carry into sleep tonight, more important than any of the specific facts about atoms or quarks or neutron degeneracy. The strangeness of the mechanism does not diminish the truth of the experience. Think of it this way. When you hear a piece of music, the sound is not some pure, self-evident thing hanging in the air. It is air pressure oscillating in complicated waves, striking a thin membrane in your ear, which vibrates tiny bones, which move fluid, which bends hair cells, which fire electrical signals up a nerve, which your brain then assembles, after the fact, into the felt experience of melody and rhythm and feeling. Nobody, on learning this, concludes that music isn't real, or that the tears it sometimes brings are somehow fake because they were caused by fluid dynamics in your inner ear. The mechanism is intricate. The music is still music. In exactly the same way, the mechanism behind touch is intricate, layered with quantum exclusion and electromagnetic repulsion and nervous system interpretation, and the touch is still touch. The blanket is still warm. The mattress is still holding you. Nothing about understanding the machinery underneath makes the experience on top of it any less genuine. There is an old habit of thought, going back at least to certain 17th century philosophers, who like to draw sharp lines between the world as it truly is and the world as it merely appears to us, that treats this kind of layered explanation as a kind of demotion, as though discovering that touch involves fields and nerves rather than simple contact reveals that touch was somehow an illusion all along, a trick the mind plays on itself. But this gets the situation backwards. The nervous system is not lying to you when it tells you the bed is solid beneath you. It is doing exactly what it evolved, over hundreds of millions of years, to do, translating a genuinely real physical event, the mutual repulsion of electron clouds, preventing your body's atoms from occupying the same space as the mattress's atoms, into a genuinely useful piece of information, namely that there is a supportive surface here, and you may safely stop falling and let your weight settle onto it. The signal is not a substitute for reality standing in for something more real. The signal is how reality reaches you at all, the only way it has ever reached anyone. This is worth extending gently, at this late and drowsy hour, to something beyond mere physical contact, because the same logic quietly applies to closeness of every kind. If someone you love is asleep beside you right now, or in another room down the hall, or in another city entirely, the closeness you feel toward them was never really a matter of skin meeting skin, in some literal, uninterrupted sense, not even when you are, in the everyday meaning of the word, touching. It was always a matter of signals, a hand on your arm, a voice through a phone line, a name appearing on a screen, each one carried by fields and photons and electrical impulses across some gap, however small or large, and interpreted by a brain that has spent a lifetime learning what that particular signal means, who it comes from, what it's worth. Contact, understood this way,
was never truly the opposite of distance. It was always a very small, very intimate distance. So small your body never had reason to register it as distance at all. Crossed by the same kinds of fields and forces that cross far larger distances too. The hand on your shoulder, and the voicemail you saved and replay, sometimes are not different in kind, only in scale, only in which particular fields carried the information, and how much of a gap they had to cross to reach you.
So perhaps the distinction between touching and not touching, which felt so absolute at the very beginning of this long explanation, back when it seemed almost troubling to learn that you never quite meet the chair you sit in, can soften now into something gentler and more accurate. There is no touching in the old, naive sense of two solid things merging into contact with nothing between them. There never was, not for you, not for anyone, not for any two objects anywhere in the universe. But there is, and always has been, something arguably richer than that naive picture, a universe built entirely from fields reaching toward other fields, forces meeting forces, information passing constantly and reliably across every gap, however microscopic, so that closeness of every kind, physical, emotional, the presence of a body in a bed, the memory of a hand once held, turns out to run on the very same quiet principle. Nothing ever quite merges, and somehow, astonishingly, that turns out to be enough. It has always been enough. It is enough for the mattress to hold you up tonight, and it was enough for every embrace you have ever received or given, and it will go on being enough tomorrow, whether or not you ever think about electron clouds again. You don't need to remember any of it now. The neutron stars can keep collapsing quietly somewhere far away, doing their strange, patient work light years from here, needing nothing from you. The electrons in the mattress can keep refusing to let the electrons in your body pass through, the way they have every night of your life, without your ever having to supervise the arrangement. Your nervous system can keep doing what it has always done, taking the honest, complicated signals of pressure and warmth and weight, and turning them into the simple, wordless feeling of being held by the bed, without you needing to check its work. All of it will carry on quietly beneath you and around you, entirely on its own, exactly as it has every single night before this one, while you let go of trying to picture any of it at all. Let your shoulders soften into whatever is beneath them. Let your breath slow, unremarkable and steady, the way it has slowed at the end of every day you have ever lived. The strangeness was only ever in the explaining. The resting was always simple. Rest well,